students, and welcome in the online session of Class 9 Science, Chapter 9 Forces and Laws of Motion. Now, this is the third video of the lesson. In the previous video sessions, we have completed Newton's first law and second law. Now, let us see what we are going to do today. Today, we'll cover Newton's third law of motion, then some examples of Newton's third law of motion, then law of conservation of momentum and the applications of law of conservation of the momentum. So let's start first with the Newton's third law of motion. Now, two laws of motion given by Newton were studied previously. This is the third and the last law of motion. So this law states that every action has an equal and opposite reaction. This is the statement of the third law of motion given by Newton. So according to this law, every action which is done by a body has an equal and opposite reaction on the other body. Okay, so every action will be done on some body and that body will definitely give some equal and opposite reaction on the first body. So now these forces act on different bodies. So for the third law of motion, there must be two bodies, two objects which are interacting with each other. So one will do action on the other and the other one will do equal and opposite reaction on the first one. But these forces, they never cancel each other. Okay, now because action and reaction, they will be opposite to each other, but they are not cancelling each other's effect. So this you have to remember, that they never cancel each other. But each force produces its own effect. So every action has its effect on the other body and the reaction also has its effect on the first body. Now, the next concept is that the force acting on the lighter body will produce greater acceleration and vice versa. If a body is light in weight, then it will be easy to give it a greater acceleration. Okay, means if a body is of, suppose here 2 kg and there is one body who is of 10 kg, suppose here it is 2 kg and here it is 10 kg. So this first body having 2 kg weight is lighter than the second body which is having a weight of 10 kgs. So it will be more easy to give an acceleration to the body having 2 kgs of weight because it is lighter in weight, so it will move faster, it will be accelerated more in comparison to the second body which is having 10 kgs of weight. Okay, so this you have to remember, that the lighter body will move with the greater acceleration and the heavy body will move with a low acceleration. And now one example here, like to walk on the ground, we push the ground backwards. Here you can see in the picture also that when we move, we push our feet on the backward directions. Okay, we pressurize at this point, that means we are pushing the ground backwards with our feet. Now as the reaction ground, now this is our action. Okay, this is the action which we are doing on the ground. We are pushing the ground with our feet. This is the action. Now as the reaction, ground pushes our foot forward. So what the ground will do? Ground will also push our leg on the forward side. Okay, so this is action and reaction. So action is given by us with our feet on the ground, and the second body is the ground which is now giving the reaction and pushing our feet on the forward direction. So using this third law of motion, we can easily walk on the ground. Fine. So this is action and reaction. They are in opposite directions. Action and reaction both are in opposite directions, but they never cancel each other's effect. Each of the force has its own effect. Okay, now in the first diagram here you can see that a person is swimming. So this swimming is also possible on the basis of third law of motion. You can see here that the swimmer is exerting pressure on the water. Fine, and the water is also exerting pressure on the swimmer. But both the action and the reaction, they are in opposite directions, but they never cancel each other's effect. Fine. So this is the action force which is given by the water. Water is applying an action force on the swimmer. So in reply to that, the swimmer is also applying some reaction by moving his hands and legs. So this is the action given by the water and the reaction given by the swimmer. So both of them help the swimmer to move forward in the water. Okay. So this is the third law of motion. Now let us move on to the next slide and see the law of conservation of the momentum. This is the new concept here now. Linear momentum we have studied in the last video also, that momentum is represented by the small letter p, and this is equal to mass of the body multiplied by its velocity. Okay, so p is equal to mv is the linear momentum. Okay, and now we have to study the law of conservation of momentum. Okay, so this name only suggests that momentum is conserved, momentum is not lost, it is conserved. Okay, so that we have to find out, and with the help of one of the examples. Okay, so let us start that this law of conservation of momentum is deduced from the Newton's third law of motion. Okay, this is given by the third law of motion, that every action has an equal and opposite reaction. On the basis of that, we are now deducing or finding the law of conservation of the momentum. So let's study with an example. So when two or more bodies interact with one another, the vector sum of their linear momentum remains constant. Fine. So what is the meaning here? That when two or more bodies they come in contact with each other, their linear momentum remains constant. Now every body which is moving has a momentum. Okay, because when the body is in motion, that means it has velocity, and if it has velocity, then it has linear momentum also, because the body has mass and the body has velocity when it is moving. So definitely the body will be having a linear momentum. But what we are trying to say here, that when the bodies are in contact with each other, their linear momentum remains constant unless and until any unbalanced force is acting on them. Okay, so let us read again, that the vector sum of their linear momentum remains constant and is not affected due to their mutual action and reaction. Fine, means whether the bodies are interacting with each other or not interacting with each other, but their linear momentum remains constant. But the only condition is that no external unbalanced force should be acting on the system of bodies. Okay, so up to when their linear momentum will remain constant? So their linear momentum will remain constant until any external unbalanced force is acting on them. So here you can see that two bodies are shown here. This is first body A and this is the second body B. Fine. So in between the first body A, it is written MA, means mass of the ball A. This is the first ball, this is second ball, right? So we have two balls taken here as example. Two bodies we have taken and both the bodies are balls. So let us see that what is MA. Fine. MA is the mass of the ball A. M is representing mass and A, because it is of ball A, so it is MA. Then MB is the mass of the ball B. Okay, MB is the mass of the ball B. Then UA. UA means, now you all know that small letter u represents the initial velocity. So UA is the initial velocity of the ball A. And UB is the initial velocity of the ball B. Fine. So these four things we have discussed now, that MA is the mass of ball A, MB is the mass of ball B, and UA is the initial velocity of ball A, and UB is the initial velocity of ball B. Fine. Now let's move on to the next slide and see. Now the condition is such that if UA is greater than UB, that means initial velocity of ball A is greater than initial velocity of ball B. That simply means that the ball A is moving with a greater speed than ball B. Fine, there we have two balls and now they are moving in the same direction. You can see here the arrows are shown in the same direction. So both are moving in the same direction. But what is the condition? That initial velocity of A is more than the initial velocity of B. So what will happen? That A will move with more speed and finally the A ball will collide with B ball. Okay, so there will be a collision between ball A and ball B. Fine. Collision means they will strike against each other. Okay. Now let this collision last for short time t. Means this collision is for a short time t. Okay, this collision finished in a short time t. So t is the time for which the collision lasts. Now during collision, suppose now when they are colliding, that simply means that ball A will apply some force on B and B will also apply some force on A, because we have studied in the Newton's third law that every action has an equal and opposite reaction. So if A strikes with B, that means A is applying some action on B. So on reply to it, now B will also apply some force on A, which will be the reaction. Okay. So during collision, suppose FAB, now here it is written FAB, means this is the force exerted by A on B. Okay, AB written means A is applying force on B. And FBA means force which is exerted by B on A. Remember children, don't get confused. Okay, the first letter, if it is written A, that means A is applying force on B. And if the first letter written is B, that means B is applying the force on A. Okay, so these are the forces which each of the body is applying on each other after collision. Fine. Now we can assume that no external force is acting on balls. Okay, so at this time no external force is acting, only both the balls are applying forces on each other during collision period. Now after collision for t seconds, okay, this we have discussed that the collision lasts for time t. So after collision, what happened? The balls move separately. Okay. So once they strike for t time, then they move apart from each other. So here you can see that this is the condition before collision. Okay, they were moving like this. But as soon as its initial velocity of A is greater than B, so they collide. So this is the scene during collision. Okay, so they came near each other and they collide. Okay, so here also you can see that during collision, A is applying force AB on B and B is applying force BA on A. Okay, so you can understand with the help of this diagram also. So this is the case during collision. But after collision, now what is the scene? That after collision, they move apart, they move separated from each other. Okay, but remember, now after collision their velocities will definitely change, because once they collide, now their velocity will definitely going to change. So what is VA now? So after collision, VA means the final velocity of A after collision. We represent the final velocity with small letter v, right? If you remember. So velocity of A after collision is VA and VB is the velocity of B after collision. Okay, so you can see here that VA is the final velocity of ball A and VB is the final velocity of ball B after collision. So in the diagram here, three of the stages are shown: before collision, then during collision what is the condition, and after collision. Okay, so before collision it was initial velocities, then during collision they are applying force on each other, and after collision the velocities change to VA and VB. Now let's move on and see. Now children, when velocity has changed from u to v, right? Initially the velocities were u and finally the velocities are v now. So if the velocities have changed, that means there will be some change in the linear momentum also, because linear momentum is mass into velocity. So if velocity has changed, that means linear momentum will also change. So let's now work out on the momentum. So change, now linear momentum of ball A will also change and linear momentum of ball B will also change. So now firstly, let's see the change in the momentum of ball A. Okay, so how we'll find now? Change means, all of you know that change means the final condition minus the initial condition. That will give you the change. So change in the momentum of A means momentum of A after collision minus linear momentum of ball A before collision. Okay, this will give you the change. Okay, so what is the change in the momentum of A? That linear momentum of A after collision minus the linear momentum of A before collision. So what was the momentum of A after collision? After collision means momentum means mass into velocity. So mass will be ma, and after collision, what is the velocity? It's va, final velocity. Okay, so this becomes ma va. Then momentum of A before collision. Before collision, the velocity was initial velocity, that is u. So momentum will be mass into velocity. So mass will be ma and velocity will be ua here. So remember here, okay. Here final is the va and initial one is the ua. So this is the change in the momentum of A. Now the next thing is the rate of change of momentum of A. Okay, so now as we are moving on to find the force applied, right? So force is what? According to the second law, what is the force? Force is the change in the rate of change in the momentum. Fine, the rate of change in the momentum is the force. So now change of momentum of A upon time taken. Rate means, I told you initially also that rate means V divided by time. Okay, so rate of change of momentum of A upon time taken. So put the values now. So change of momentum of A will be MAVA minus MAUA. You have find it out here. So you have just put the values here. Upon time taken is T because collision lasted for T seconds. Okay, so this is the rate of change of momentum in ball A. Now we all know that this is equal to the force applied. Now rate of change of momentum. Okay, rate of change of momentum means change in the momentum of A upon time. This is equal to force, as we have studied in Newton's second law of motion. Okay, so now this force will be, because this force is applied by ball B, because we are studying the change in the momentum of A. So why the momentum of A changed? Because B ball has applied some force on it. So this force applied means this change in the momentum of A upon time will be equal to the force. But which force, students? This force is applied by ball B. Okay, so this is equal to the force exerted by B ball on A ball. So this is equal to FBA, means force applied by B on A. Fine. So this we have deduced for change in the momentum of ball A is equal to the force applied by ball B on A. So this become equal to this one. Okay, I hope this is clear to you all, and this is our equation number 1. Now let's move on to find the rate of change of momentum of ball P. Now during collision, momentum of A also changed and B also changed. So we have find for ball A. Now let's find for ball B. So what will be the rate of change of momentum of B? So as we have find for A, similarly we have to find for B. So what will be the change in the momentum of B? That means momentum after collision minus momentum before collision. Okay, so this will be MB VB minus MB UB, as we have find for A. Similarly you will write for B upon time. Okay, so now this rate of change of momentum in ball B, this is due to the force applied by ball A. Okay, so this will be equal to force applied by ball A on ball B. So this will be equal to FAB. Okay, so this will become equal to this. So this is our equation number 2. Okay, I hope these equations are clear to you all. If you have studied second law of motion clearly, this will be very easy for you to understand. Now let's move further. So we have now equation number 1 and equation number 2. And you all know that every action has an equal and opposite reaction, means the force applied by B on A should be equal to the force applied by A on B. Fine, means if this is A ball and this is B ball, force applied by A on B should be equal to the force applied by B on A. Fine. So at last what we have to do now, we will do that this force applied and this force applied both should be equal and opposite to each other. So let's do that. Now according to Newton's third law, the force FAB exerted by ball A on B and the force FBA, that is exerted by ball B on A, must be equal and opposite, because this is according to the third law of motion. So finally what we are doing, children, we are just equalizing both the forces. FAB is equal to minus FBA. Why we have put minus sign here? Because equal and opposite. Okay, every action has an equal and opposite. Opposite means if this is positive sign, so here will be negative. Opposite to each other in direction. That's why one is given by minus sign. Any one of them you can take on either side. So putting the values of these, Force exerted by A on B is equal to this value you have found previously, and this will be equal to minus FBA, force exerted by this. Okay, so now if you remove time and time from both the sides, what you will get, children? MBVB minus MBUB, that means change in the momentum of ball B, is equal to minus sign change in the momentum of ball A, means you have removed time section from both the sides. So you will get this equal to this one. Okay, so this is the equation now. Now, if you interchange these, you will get this one. Okay, so what we have to do, AA terms means this final terms we have to take on one side. Fine. See, this is minus. If you take it on other side, it will become plus, and this is also negative. This is also negative sign, you can see here. This you take on the left hand side, so it will become positive. Fine. So that is really done here. So MBVB. Okay, so MVBB here. Then this minus MAVA has come onto left hand side, so it becomes positive here. So MAVA means what now? Change in the momentum of ball B after collision and change in the momentum of ball A after collision. So one side we have taken the change in the momentums of ball A and B after collision, and this is the linear momentum of ball B and linear momentum of ball A before collision. And you can see here that this is equal to that side. That means this is equal to this side. Means what? Linear momentum after collision of both the balls is equal to linear momentum of both the balls before collision. So what is the conclusion, children, here? That the momentum before collision and after collision remains the same. Okay, so this is what now? This term is total momentum of the balls after collision, left side, and total momentum of the balls before collision on the right hand side. So therefore the total momentum of the two balls remains unchanged on collision. So during collision or after collision, the momentum remains the constant. Okay, so this we have concluded that the linear momentum is conserved or remains the same or remains constant until and unless any external force applies on it. And here we have assumed that no external force is applying, so we have proved here that the linear momentum after collision and before collision remains the same. There is an equal to sign in between, so it remains the same, and this is called the law of conservation of momentum, that the momentum is conserved, it is not going to change. So this is the law of conservation of momentum. Okay, I hope the law is clear to you with an example. Student, this topic is also very important. It comes for 3 marks, and to derive it, okay, derivation, you have to find this final conclusion by putting the values as we have done with the help of this example. It's very simple. If you have learned the second law of motion, and what is second law of motion? That force applied on the body will change the momentum of the body with time. Okay, so change in the momentum of the body upon time is equal to the force applied on it. That's simple, and just you have put the values of the two balls and you have just equalized them. Nothing we have done, but if you will read it 2-3 times, you will definitely come to know about it more clearly. Okay, so this is law of conservation of momentum. Now let's move on to the applications of law of conservation of momentum. Let's see some of the applications where this law is applicable. Okay, so now flight of jet planes and rockets can be understood in terms of law of conservation of momentum. So before firing, the momentum of rocket is 0. Means before starting the engine, the momentum of the rocket is 0, because there is no velocity. Okay, because the rocket is at rest position. So on firing, the burnt gases rush out as soon as the engine is started. In the rockets they leave the gases from the backside of the body. So on firing, the burnt gases, when the fuel is burnt, the gases which are formed after reaction, they rush out through the nozzle in downward direction. Okay, so if suppose this is the rocket, fine. So rocket has a tail, and when the rocket starts moving in upward direction, the gases come out, the hot burnt gases, they come out from the backside. Fine. So gases are moving in this direction, rocket is moving in upward direction, rocket in this direction, and gases in downward direction. So the rocket moves such that the momentum of rocket plus the momentum of escaping gas is equal to 0. And we know that when no external force is applied on it, so there are two bodies here, one rocket and gases, right? So the linear momentum of both of them remains constant. So what can we write? That momentum of rocket and the momentum of the gases which are coming out is equal to 0. Is equal to 0, and if you now turn this equation, what you will do, here it is 0. So what you have to do, if you take this term, momentum of escaping gas, on the other side of equal to sign, then it becomes negative, right? So momentum of rocket is equal to minus momentum of escaping gases. Okay, so this is what now, that the momentum is conserved. There is an equal and opposite reaction here, and the momentums are conserved. Okay, minus sign shows that they are moving in opposite direction, so the momentum is conserved. You can see here the momentum of rocket and the momentum of escaping gases, they are equal with this sign. And why minus? Because they are in opposite direction, right? So this proves the Newton's third law also, and the law of conservation of momentum also. So it's a very good example you can quote wherever you want to give for Newton's third law as well as for the law of conservation of momentum. Now similarly, recoiling of gun can be explained in these terms of laws. Okay, recoiling of gun. So when the gun is shot, so bullet is fired, right? So bullet goes in this direction, but the gun gets a jerk in the backward direction. Okay, so recoiling of the force on the gun means the gun shifts on the backward direction. There is a jerk on the back side. So this is also what? This is the action and reaction on the opposite side, and here also the conservation of the momentum can be seen. Okay, now let's move on to the next slide now. Okay, that's summary only. So what we have done, children, so we have studied today about Newton's third law of motion. I hope this is clear to you all, that every action has an equal and opposite reaction. Okay, and these both actions and reactions are working on opposite bodies, on different bodies, and action and reaction, they never cancel each other's effect. So each one of its effect is maintained, right? And secondly, we have studied about the law of conservation of momentum. Okay, so it is written m1 u1. m1 means mass of the first body and initial velocity of the first body. As in the example, we have taken ball A and ball B. You can take bodies 1 and 2 also. So this is the momentum of the bodies before collision, and this is the momentum of the bodies after collision. Right? After means some of the happening. So in both the cases, momentum before collision and momentum after collision is conserved, is the same. Fine. So that means it is conserved. So this we have studied in today's session. I hope the topics are clear to you all. And here we come with the end of the lesson also. So after completion of the lesson through videos, we are going to take the Google Meet also for taking the complete revision of the chapter. Till then, you all do read the lesson, please. Okay, do read the lesson, get ready with your, if you have any doubts, you can ask in the Google Meet also, and do complete your notebooks as well. Okay, so we'll meet in the Google Meet then afterwards. Till then, all of you stay home and stay safe.